three modes we have discussed, related equations also we have discussed. Now today we will discuss the characteristic of common base. Okay, later on we will go for common emitter and common collector. So common base characteristic means current and voltage characteristic. Like diode we have seen, and we have discussed about the diode operation. After that we have discussed the IV characteristic of diode. Here also the transistor characteristic means current and voltage characteristic. So different from the diode, here two type of characteristic we will see. In diode we have only seen one characteristic, means when we increase the voltage, how the current will change, that we have plotted with one graph, exponential increasing function. So that is the IV characteristic diode. But here we will plot two characteristics. One is input side characteristic, other one is output side characteristic, because transistor is a three-terminal device. Okay, so first we will discuss common base. So for common base configuration, we have to draw the circuit diagram. So how you have to draw, I already told you in the last class. So first you have to draw the transistor symbol and orient such that it will be, the base side will be in the bottom side. Okay, so let us take PNP transistor. So I have drawn the PNP transistor. Now this is your base, this is your emitter, this is your collector, and this side I will give input, this side I will take output. Okay, now I have to bias the transistor to make the circuit. So first I will connect one resistor here across the emitter, that is RE, and emitter base junction should be forward biased. So this is your P, this is your N, this is your P. So what I will do, P side should be connected to higher potential, N side should be connected to lower potential, and I will name as VEE. Okay, to measure the potential between emitter and base, let us connect one voltmeter, and the name is VEB, which will be between this emitter and base. Okay, and if you want to measure the current, you can connect one ammeter here to measure the corresponding current, how much current is flowing. So how much current is flowing here, this is your emitter current IE. So left part is complete. Now we'll go for right part. So here also same thing, we'll connect one resistor, that is RC. Then P side collector base will be reverse biased, so P will be connected to negative and will be connected to positive. Name as VCB or VBC, depend upon the voltage. Now I will connect one potentiometer or voltmeter to measure the voltage between base and collector. So base and collector voltage to measure, and to measure one current, we have to connect one ammeter. So this is the diagram of CB configuration. Okay. Once you do that one, then we have to see how we'll go for input and out characteristic. So this side is your input side and this side is your output side. Now here, look at the input side, will have current and voltage, means VEB, change in VEB, that means emitter voltage, emitter base voltage, if you change, what is the effect on that on emitter current, that will give you one characteristic. Similarly, output side, if I take the voltage is VBC or VCB, so if you change the base emitter, base collector or collector base voltage, then what is the effect on output current? So what is my output current here? This is your IC. Okay. So that again give you another plot which is called as output characteristics. So basically, if you consider input side and plot the graph between voltage and current, that is your input characteristic. If you consider output side and plot the graph between voltage and current, then that is your output characteristic. Okay, so in detail, let us discuss. So first we'll go for input characteristic of GB mode. So what I'll plot between VEB and IE. If I change VEB, what is the effect on IE? I want to plot, but this is depend upon this IE depend upon VCB, because if you more reverse bias at the collector side, it will attract more number of holes, so IE will increase. So for particular case, I'll fix the VCB. Suppose I'll fix VCB to let us take -1 volt, then I'll increase VEB from 0 to 0.1, 0.3, 0.5, 1, 2, 3, 4. Then I'll observe what is the IE for one set of graph. Then I'll change this -1 VCB -1 to -3 volt. That means I have increased reverse bias voltage across collector and base. Then again I'll start increasing VEB and observe IE. So that is another set of graph. Okay. So similarly, 3-4 graph you have to plot in a single diagram so that you will get the input characteristic. So let us understand first. If you look at here, emitter and base, this is like a PN junction or not? Emitter is P type and base is N type. This is like a diode connection. Yes or no?
Yes, sir.
Now, in diode, if you increase the voltage, the current is increases exponentially, right? Up to threshold voltage, less current. After that, current is increases exponentially. So here also the same type of operation will have, because this is like a PN junction diode. When I increase VEB or emitter base voltage, then if I take this is silicon diode, then up to 0.7, the threshold voltage is 0.7 for silicon. So up to 0.7, current is less. Then after the current will increase. So let us first plot the x-axis and y-axis. So this is my x-axis, y, and this is 0. So x-axis I'll take V EB. See here, emitter is positive, base is negative, plus minus. So emitter potential is higher compared to base. So that's why I have taken here VEB positive side, and y-axis what I want to measure, emitter current IE. IE in milliampere and VEB in volt. Now at that instant, let us assume the VCB -1 volt. Okay, first I want to plot VCB -1 volt. Then I'll start increasing VEB from 0 to higher voltage. Then I'll observe what is my IE. Then I will plot the graph. Now, due to this forward bias PN junction between emitter and base, the characteristic will look like diode characteristic. Okay. So the characteristic will be like this. Up to this, current is very small. After that, current will increase exponentially. So I can write this is your VCB -1 volt. Yes or no? Are you getting why it is exponentially increasing? Because emitter base junction is like a diode junction and it is forward bias, so the characteristic will look like diode characteristic. Okay. Now when I increase VCB, what will happen? Increasing VCB means we are giving, if you look at the diode junction then this is your PN junction, what I told you. Okay, so this is your PN junction diode. So what we have named as, this is your emitter, this is your base, emitter, base. So this junction is forward biased, means current is flowing from here to here. So exponential increase. So this is the diagram we have plotted. Now when I increase VCB means this is your collector, this is your base. So collector is negative, this is positive. So when I increase VCB, that means I am giving more negative potential to the collector side, and that will attract more force towards the collector side due to negative potential. So IE current will increase. Or another way you can understand, two concepts we have already discussed. When VCB increases, what happened to the depletion region across collector base junction? Wider or narrow? If the junction is reverse biased, the depletion region is more or less? Or more? More. Suppose initially I have taken VCB minus 1 volt and the depletion region is like this. Okay, this is your depletion region. Now I am increasing to minus 3 volt. So depletion region will increase. I am increasing reverse bias, means the depletion region will increase. Now my depletion region is increases. Right. Now what happened to the base width? Earlier the base width is from here to here. Okay. Now base width is here to here. If I take forward bias junction is little bit depletion region, narrow depletion region, then also what happened to my depletion region? What happened to the base width or effective base width? When I increase VCB, the base width is decreases or increases? Decreases. Actually, if I take a diagram, look at here. So this is your okay, P N P, and this is your forward bias junction. Reverse bias junction is this one. So when I take VCB, okay, let us take VCB minus 1 volt. So this is your depletion width. Now when I increase VCB to minus 3 volt, the depletion region is increases. Now here to here, this is actually your base width, but out of that, inside the depletion region, I will not find any mobile charge carrier. So effectively, I will find the carrier within this region only. Okay, so this is called as, this is the actual base width, and this one is called as effective base width, where I can find the carriers. Okay, now due to increase in VCB, what happened to the effective base width? Earlier this one, now my base width is from here to here. See the green line and green arrow and the blue one. The effective base width is increases or decreases? So decreases. Effective base width is decreases. This is called as base width modulation. Base width modulation. By increasing collector base voltage, the effective base width is decreases due to increase in the depletion region between collector base junction is called base width modulation, or this is also called as early effect. Okay, early is given by the name of scientist J.W. Early. So he has first detected this phenomenon. So the name is given as early effect. Okay, or base width modulation. Understood?
Yes, sir.
Now, holes are moving from here to so when I talk about current or emitter current, I will get due to diffusion. Okay, due to diffusion, the current will moving from P side to N side initially. Okay, uh, that means this diffusion current is depend upon the concentration gradient, that is dP by dx. If this distance or width is decreases, then obviously the concentration gradient will increase, denominator will decrease, means the whole term will increase. This will increase means the emitter current will increase. Okay, so emitter current is increasing when I'm increasing the VCV. You can think like that. Also, you can understand when I increasing the VCV, that means I'm giving more negative potential to the collector side, so that more and more holes will reach to the collector and they are attracted from the emitter side. That means it is enhancing the emitter current. So when I increase VCV, then emitter current will increase. Okay. So here VCE I have taken -1 volt. So if I take -3 volt, then the graph will the current will increase, means the graph will shift upward or downward, or slope will increase or decrease. Slope will increase or decrease. What we have discussed here, when VCB is increasing, IE increases. Okay, increases means we have plotted one graph like PN junction diode. It is the junction is like that, so the characteristic will be exponential increasing function. Now, when I increase VCB graphically, if I want to plot the same way, the characteristic also will see, but the graph will shift upward or downward. Current is increasing means upward.
Upward.
That means slope is enhancing. So next graph will be like this. Next graph will be like this. Okay. So here I can write VCB -3 volt. Here I can write VCB -5 volt. Okay. So current is increasing. So how you will know, those who are confused little bit, you can see for particular voltage, suppose I want to plot the current at particular voltage. See here. Okay. So this is the point where it is meeting. Right. So let us take I1, here I2, here I3. Okay. Now I1 is greater than I2, greater than I3. For particular VEB, suppose VEB is let us take this is 0. 0.3, 0.5, 0.7. This is 1 volt. Okay, 1.5 volt, 1.7 volt, 1.9 volt, like that you can increase. So at 1 volt, if I observe VB at 1 volt, then I am getting the VCB minus 5 volt giving more current compared to VCB minus 3 compared to VCB minus 1. Is it clear for all? What is base width modulation? Why current graph is like diode characteristic, and if we increase VCB or more reverse bias the collector base junction, why emitter current is increasing? Is it clear for all?
Yes, sir.
Yes, sir.
So input side we have discussed. Now we'll go for output characteristic. Okay. So output characteristic means let us see the diagram again. Circuit diagram. Output characteristic means output current and output voltage. If I change output voltage, what is the effect on output current? You have to observe when input should be fixed. Okay, input current must be fixed, because if I increase or decrease the input current, then obviously IC will change, because IC equals to alpha IE. Okay, so that's why if we fix input current, then observe what is the change in output voltage on IC, then you can plot output characteristics. So output voltage is my VCB, or if we want to plot positive side, so VBC in volt, and output current is IC in milliampere. It is 0. Okay. Now come to this diagram. Here, when we have open circuited the emitter base junction voltage, what is my current? What current I'll get? This is your IC. If you go back to the current component graph we have discussed, this one. IC equals to this plus this. Yes or no? We have discussed. Now, if I open this emitter base junction, can I get this ICP? ICP means what? Holes are pushing from emitter and collecting at the collector. If I am not giving any positive potential at the emitter, can holes will move to collector, emitter holes?
No, sir.
No. So IC will be only due to the leakage current, that is ICO. So what I am trying to explain here, the characteristic or output characteristic when you plot, we have to fix the IE. So IE 0 milliampere, 1 milliampere, 2 milliampere, 3 milliampere, like that you have to fix. Then you increase the VCB and get the or observe the output current as IC. So when IE is 0, then how much current I'll get? Only leakage current I'll get. So that current, let us, this one, when IE equals to 0 milliampere, this is your leakage current. Okay. IE 0 means input emitter base junction is open circuited, so we are getting only leakage current. So IC equals to how much? IC equals to this much. So IC equals to alpha IE plus ICO. So this is 0. So I am getting IC equals to ICO. So that is very small amount. So that's why this is the representation. Is it clear? Is it clear?
Yes, sir.
Now I'll increase this IE to 1 milliampere. That means increasing the emitter current by fixing the VEB to certain voltage. I'll fix this VEB certain voltage so that this IE will be 1 milliampere and I am increasing the VCB. Now when I increase the VCB, initially what happens? The holes will slowly move from here to here. As I increase more and more negative potential, more and more holes will reaching at the collector side. Yes or no? So I am starting from 0. When I increase the potential, then slowly the current will increase. Okay. When I increase this one, what is the maximum limit? I am fixing this 1 milliampere here. Input is fixed. So what is the maximum current I will get here? IC equals to alpha IE. Okay. Alpha is less than 1. So if IE is 1 milliampere fixed, then how much maximum IC I will get?
Sir, alpha.
Alpha.
Sorry, sir, one.
Less than 1, because alpha is less than 1 means 1 milliampere into less than 1 term means it will be less than 1 milliampere or nearly about, because alpha is 0.95 or 0.995 like that. So we'll
Sir,
get
approximately 1 we can take.
approximately or little bit less than that we'll get. So when I increase, then it will increase, but maximum this type of, or if I observe here, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. If I label it, then it will be little bit less than 1 milliampere I'll get. So IE equals to 1 milliampere. Now if I take another condition where I'll fix IE to 2 milliampere. Okay, I'll fix some voltage here so that 2 milliampere current will flow across emitter current, and I'll increase this VCB from 0 to higher voltage. Then what I'll get? Maximum 2 milliampere like this I'll get. So current will initially increase, then like this. So IE equals to 2 milliampere. Similarly, all the graph you can plot. Okay, IE 3 milliampere, IE 4 milliampere, IE 5 milliampere. Like that you can increase. So this is your output characteristics. Understood? Any doubt from this output characteristic?
No, sir.
Okay. Now we'll see how this is the graph, but this graph is again divided into 3 to 4 parts. We'll see that one. Understand here. This region where I am getting the leakage current. Okay, I am getting the leakage current. That is called as cutoff region. Okay, that is called as cutoff region. So now look at the figure here. In the cutoff region, what I have set IE as 0 milliampere. That means this voltage is open circuited. then only I'll not get any emitter current, yes or no? If I'll not give any positive voltage here, then holes will not move to collector side, so that IE will be 0 milliampere. हाँ कि नहीं? How I'll set IE 0? How I'll set IE to 0 milliampere? It will be open circuited.
Yes, sir.
Or negative, or morely means I am not giving any positive voltage to this, then only I'll get 0 current in the emitter. And what about the collector base junction? Collector base junction, I am moving from here to 0 to higher voltage. Let us take 0 point, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. That means VBC I am giving. So VBC means minus of VCB. So I am giving reverse voltage here. So tell me, emitter base junction which type of biased and collector base junction is which type of biased for this condition? Emitter base junction is open circuited, or I can say reverse biased, and collector base junction is also
Reverse bias.
reverse biased. So when both the junctions are reverse biased, then we are getting leakage current, and this region is called as cutoff region. Okay, it is called as cutoff region. So this is your cutoff region. Now from here to here, this is called as active region. Okay, so in active region, current is flowing, we are getting current. Current means this should be forward biased, that means this is positive and holes are pushing from emitter to collector, and at the same time VCB is negative, so that they are pulling the holes from the emitter towards the collector. So emitter base junction is forward biased, collector base junction is reverse biased, in which we are getting the normal operation of the transistor. Yes or no? So emitter base junction forward biased, collector base junction reverse biased. So this is your active region. Okay, is it understood? Now let us extend this to left hand side. Okay, if I extend this one, then what will happen? VCB, I am giving negative voltage here. Okay, if you look at here, this is your PNP. So N is connected to P is connected to negative, N is connected to positive. So this is your VBC positive. If you take VCB, then it will be negative. Okay, VCB negative, VBC positive. So you look at here, I have taken here VBC, that's why I have taken here positive things. Now same case, if I take VCB, then what I will take? 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7. Like that I have to take. Agree or not? VBC equals to what? VB minus VC. VCB means what? VC minus VB, potential difference between base and collector. So potential at base minus potential at collector. If I want to measure VCB with respect to collector, then VC minus VB. So if I write VBC, that will be minus of VCB or not?
Yes, sir.
So same thing I have written. If I take VBC as my voltage, then I have to consider positive. If I take VCB, then I have to take negative. Okay. But thing is clear. We are giving VCB as negative voltage. So because I have plotted in the right hand side, that's why I have represented as VBC, which is showing positive. Now, if I want to represent this VCB in left hand side, then it should be positive. Or if I want to represent VBC in the left hand side, then it should be negative, because 0 left hand side means negative, right hand side positive. Similarly, if I want to represent VCB, then right hand side it is negative, means left hand side it should be positive. Axis in reverse mode it is taken. Okay, any condition you can take. So if I want to represent VBC, it should be -1, -2, -3, -4. If I want to represent VCB, then +1, +2, +3, +4. Anything you can take. Okay. But ultimate thing is that VCB positive means what? Look at here. VCB positive means I should connect like this. Yes or no? When I am taking VCB negative, then this junction is for reverse bias. P side will be connected to negative, N side is connected to positive. Now VCB forward bias means P side will be connected to positive, N side will be connected to negative. So I am giving positive potential at the collector. So when holes are moving from here to here and see this positive potential, they will move towards the collector or they will repel from the collector side. What will happen? When I have taken negative potential at the collector, they are attracting holes. Now I am giving positive potential towards the collector. So what will happen? The holes will attracted by the collector or they will repel back?
Repel back.
They will be repel back. So this positive potential will repel these holes towards the opposite side. Now when I increase this positive potential more and more, then whatever current I am getting here, that will reduce because holes are moving in opposite way. It is not collecting at the collector. So after some time, the current will decrease to 0 or not? So current is
Yes, sir.
decreasing. At some time it will decrease to 0. So this area is signifies positive potential to the collector. CB is positive or forward bias PN junction diode, means the holes, whatever magnetic area here, they will be moved to the N side, so that whatever current is flowing, that will reduce, and at some time or some voltage, they will reduce to 0. So this is the potential at which the current will reduce to 0. Okay, these are the points. So this region is called as saturation region. Okay, so in this saturation region, what happened to emitter base junction and collector base junction? Both are forward biased or not? You look at this PN junction, P is connected to positive, N is connected to negative. Emitter base junction is forward biased. Look at the collector base junction, P is connected to positive, N is connected to negative. This is also forward biased. So for saturation region, emitter base junction forward biased, collector base junction also forward biased. Then this is called as saturation. Yes or no? So three regions we have seen. Cutoff region, emitter base junction is reverse biased, collector base junction is reverse biased. Active region, emitter base forward biased, collector base junction reverse biased. Saturation, both are forward biased. Okay. Another region is also there, which is called as breakdown region. So see, suppose the transistor is operating in active region. That means emitter base junction is forward biased and collector base junction is reverse biased. And I'll increase this voltage up to what figure I have shown, up to 6.5 volt. Now if I move this way by increasing the VCB 7, 8, 9, 10, 11, 12, that means I am increasing the VCB or reverse bias voltage I am increasing. Now look at here, this junction, this is like a PN junction diode which is reverse biased, and I am increasing the reverse bias more and more. Okay, I am increasing the reverse bias. So diode working in reverse bias condition and increasing the reverse bias more and more, then what will happen? PN junction diode we have seen, when diode is operated in reverse condition and increasing the voltage, after certain voltage, what will happen? Diode characteristic, this is the forward characteristic. Reverse characteristic means this one. If I increase the voltage more and more, then what will happen? What is this point? तुम लोग शायद पढ़ते नहीं हो, कुछ तो रिप्लाई नहीं दे रहे हो ना, जैसे जैसे आगे जा रहे हैं वो पीछे का सब भूल जा रहे हो. What is this point? The
breakdown.
Huh?
Breakdown voltage.
V voltage.
EBR, right? So when I increase reverse voltage, then after a certain point, the current will increase heavily. That will break down the diode. So same thing is happening here. This is your PN junction diode, and this junction is reverse biased. P is connected to negative, N is connected to positive. Now when I increase more and more reverse bias voltage by increasing the VCB, then what will happen? Suddenly the huge amount of current will flow and that will break the transistor. So we should always avoid this region. So this region is called as breakdown region. Okay, this region is called as breakdown region. Generally we avoid this breakdown region, and to operate the transistor in for amplifier, as an amplifier, then we have to operate the transistor in active region. This region of operation is very, very important. So we have to make sure my transistor is operated in this region so that it can act as an amplifier. Cut means current zero. Saturation means also we are not getting current. So active region we have to operate, and breakdown region also will avoid. So to act as an amplifier, the transistor must operate in the active region. Okay. So this is the input and output characteristic of common base configuration, and next class we will discuss for common emitter configuration. Any doubt you can ask me. So we may get a long question like draw the input output characteristic of NPN transistor in common base mode or PNP transistor in common base mode. So PNP or NPN transistor means you have to only take the sign convention, how we will connect the voltage so that it will be forward bias, reverse bias, and what is the current direction you have to note it, and this VCB and VBC will be a little bit changed. and you have to explain what is base width modulation, why like input characteristic we have seen. When VCB increases, then IE increases. So what is the reason? Like I have explained here, base width modulation, and due to that IE current increases, you have to explain. After that, for output characteristic, you have to check, you have to explain in cutoff region, emitter base junction is open circuited and or reverse biased, then current is not flowing, only leakage current is flowing. So that is cutoff region. Active region means when you set I 0, 1, 2, 3, 4 like that, current is increasing and maximum current should be less than the input current, and it is parallel to the x-axis. And in this region, emitter base junction is forward bias, collector base junction is reverse bias. You have to explain on your own language. Similarly, saturation region, breakdown region, you have to explain. Okay.
Sir,
Hmm.
sir, this will not come in the midsem, right?
No. This is for end sem. Mid sem,